Okay, so question number 3. Classify the following as polar or nonpolar. So to answer this question, we need to just draw all of the different Lewis structures of these molecules, and then from there we can try to figure out if they're polar or nonpolar. So first, let's find the total valence electrons for our first molecule. I think this is germanium. We hardly see this element, so that's why I'm kind of hesitant on what it's called, but this is germanium, I'm pretty sure. And look up a periodic table. It is found right here, atomic number 32, in 14, in group 14, so it has 4 valence electrons. And for hydrogen, hydrogen has 1 valence electron, and we have 4 hydrogens, so we just multiply this by 4. And we should just get a total of 8. So if we draw out the Lewis structure, we have our germanium in the middle. And then we just have our 4 hydrogens single bonded. And if we count out all the electrons I've drawn so far, you'll see that I already have my 8. And you'll also see that everything is symmetrically around the germanium, all the hydrogen atoms. So therefore, this molecule is nonpolar. So you can see that I didn't even need to calculate for electronegativity. Even just the fact that it's a symmetrical molecule, I could say that this is a nonpolar molecule. Because even if there was a difference, then they would all just cancel each other out. Okay, so on to our second compound. We have water, H2O. Okay, so again, hydrogen has the 1 electron multiplied by 2. Oxygen has 6 valence electrons. And we get a total of 8. So now let's draw oxygen as our central atom. And then we'll have our 2 single bonded hydrogens. So you'll see that when if we recall that each bond contains 2 bonding electrons, that means I only have 4 electrons in this structure so far. So for the remaining 4, since we need 8 in total, I'm just going to place them as lone pairs on my oxygen. So now notice that we have this bent structure. So it's not linear. And also, oxygen is more electronegative than the hydrogens. So we are going to see a dipole moment going towards the direction of oxygen. And because of its bent structure, it doesn't really cancel out or anything. So we're left with this partially negative side and partially positive side of the water molecule. So this is what makes water polar. Therefore, polar molecule. And this is because this dipole moment isn't cancelled out due to this structure of water. So now let's do our last molecule, which is carbon dioxide. Carbon has 4 valence electrons. Oxygen has 6. And we have 2 oxygens. So 12 plus 4 is 16 electrons in total. So now we'll show our carbon in the middle as our central atom. And then if we were to draw two single bonds to oxygen, then our carbon wouldn't have a full octet. So then we can just make these double bonds. And we only have 8 electrons in this structure so far. So we need 8 more, and the last 8 will go on my oxygens. Okay, so now for the case of, for this molecule, our oxygens are still more electronegative than carbon, so there's going to be dipole moments going towards the direction of the oxygens. But this time they cancel each other out. So we have a linear molecule. And these dipole moments cancel out. And when that happens, we have something called a zero net dipole moment. So therefore, we can say that CO2 is nonpolar. Okay, so now let's see what the junior tutor said. Polar molecules are those that have an electronegativity difference between the bonded atoms. On the other hand, nonpolar molecules are those that have electrons that are shared equally between atoms. There are also nonpolar molecules that have polar bonds in a larger molecule that cancel each other out. So for our first molecule, it's nonpolar. And they also calculated electronegativity difference between the two. And it says, though there's some electronegativity difference, the polar bonds cancel each other out due to their molecular geometry. For water, it's polar. And it says, though the overall charge of the molecule is neutral, orientation of the two positively charged hydrogens at one end and the negatively charged oxygen at the other end gives it two poles. So it's not actually positively charged like these aren't ions. We refer to them as partially positive. So I'm just going to kind of fix the wording for the second explanation. And for CO2, though there's an electronegativity difference between carbon and oxygen, the polar bonds cancel each other out due to the molecular geometry. Okay, so this solution is correct. For H2O, the hydrogens have a partially positive charge and the oxygen has a partially negative charge. Since oxygen is more electronegative and for CO2, the dipole moments cancel each other out. Okay, so the solution is still correct.